Hey there, and welcome to another calculus video sponsored by COVID-19. If you don't want to go anywhere or do anything, then we got you covered. Anyway, sorry, I'm getting giddy. Anyhow, section 311, last chapter 3 section that we'll be doing. Going to take a look at related rates. This is an introductory video. There will be a second video that just pretty much works problems. I'm going to do an example or two here, and not everybody may need to watch that second video. It'll just give you some additional examples to kind of work things out to make sure that you're following along. But we'll do a couple of examples here. Anyway, let's get started. So what's the idea of a related rates? Related rates is this concept that every variable pretty much can be thought of as dependent upon time. Okay, so example, y equals x cubed minus 2x squared minus 5x plus 4. Normally, the way we think of this is that x is the independent variable and y depends on x. All right, but what we're really going to think about now is not that idea, but the fact that both x and y are dependent upon what time it is. So if you look at the graph of this function, here's the graph of y equals x cubed minus 2x squared minus 5x plus 4. It's stagnant, it's not doing anything. But if you pick a point on this graph and then as time goes along, think about this point moving along this curve. So think about this as like a road, and you can model the layout of the road with this graph, but then where a car's position on the road is depends on the time of you checking, right? And so you map out that graph as a stagnant graph, but then you can think about the position of where you are, how is this car changing position as it moves from here up to here, or around this curve, or down this way, or back up this way, or whatever. Okay, so that's the idea of a related rate. And so basically here's the concept. The concept is that t, which stands for time, is the independent variable. It's what's changing and making everything else change. So x depends on t and y depends on t. And so when we want to find the derivative of something, we take the derivative now, it's implicit, and it's with respect to t. And we do it just like we did other implicit differentiation. We take the derivative with respect to t of each piece. But just like when we took the derivative of y with respect to x, we had to use the chain rule because x was inside of y. Here, t is inside of both of these guys. And so if you want to differentiate, the derivative of y with respect to t is dy dt. The derivative of x cubed with respect to t is 3x squared times dx dt. Because again, we're not taking the derivative with respect to x, we're taking it with respect to t. Minus 4x times dx dt minus 5 times dx dt. And then of course 4 is a constant, it's just derivative is still 0. But you'll notice that the relationship here, dy dt, what does dy dt represent? This represents the change in y. In our problem, it represents how quickly the point is going up or down on the graph, north or south. Okay. What does dx dt mean? Dx dt means the change in x. So this means how quickly it's moving left and right on the graph. And so your changes are related to each other. The rate of change of the y is related to the rate of the change of the x because the dx dt and the dy dt are in an equation together. So that's where related rates, the idea of related rates comes from. Okay? And so let me show you a more specific example. All right. So let me show you what we can do with this and the questions that can be asked. So question number 1 here. How fast is a point on the graph of our function y equals x cubed minus 2x squared minus 5x plus 4, moving up or down if the point is constantly moving to the right at 2 meters per second at the time when the point is at 0, 4. Okay, so if you go back to the graph, the point 0, 4 is on the graph, and as x moves to the right, y goes up and down and up, right? The point goes up and down and up. So what's really happening here, we're saying that dx dt, the point is moving to the right. Dx dt is a constant 2 meters per second. And that when x equals 0 and y equals 4, we want to find how quickly up or down dy dt, right? We want to find how quickly up or down y is changing. So what do? We come back up here to this equation and we plug in for all these variables. We plug in for dx dt and x, and we figure out what's going on there, okay? So if we plug in for dx dt and for x, wipe these out here, this will make it easier. Okay, dy dt is 3 times 0 squared times 2 minus 4 times 0 times 2 minus 5 times 2 plus 0, and then we get 0, 0, minus 10 and 0, and so dy dt is negative 10 meters per second. So that means it's moving down, right? Because it's negative. Negative y is down. It's moving down the graph at 10 meters per second compared to it moving to the right at 2 meters per second. And you can kind of see that that would be true. If we're coming up, then we're coming back down, right? It makes sense that we're moving down at least, and because it's so much steeper here, we expect the change in y to be significantly larger than the change in x. Okay? So that's the idea. Let me do another problem for you. Okay, so here's the idea. We've got a 10-foot ladder leaning against a building, and you are climbing up on that ladder, and as you get to the top of it, it's not secured and it starts to slide away from the base of the wall. So the distance from the ladder to the base of the wall, we're going to call that x. And the distance from the top of the ladder down to the bottom of the ground here, we're going to call that y. So what we have here is we have a little triangle, right triangle, and we said it was a 10-foot ladder, so that side's constant. So we know that x squared plus y squared equals 10 squared. That's just a fact of the Pythagorean theorem, right? Right triangle. But that also gives us a relationship between x and y that we can differentiate with respect to t in order to figure out how, if this starts moving away from the wall at 3 inches per second, then how quickly is it moving down the wall? Right, how quickly is it moving down the wall when it hits 3 feet? Okay. Well, what you got to do is you can differentiate this once again with respect to t. So we get 2x, x prime, or dx dt. Now you know why we use the dx dt and the dy dt instead of the primes. The derivative of y squared is 2y dy dt. The derivative of 10 squared, 0, right? Don't bring down the 2, it's just a constant. And so what are the things that we know? Well, we know that y is equal to 3 feet. We're looking for dy dt, and x dx dt is equal to 3 inches per second. Wait a minute, this is feet, this is inches. I can't do that. I got to change this into 1/4 of a foot per second, right? Divide by 12, 12 inches in a foot. And so I got to replace that. Careful, make sure your units match. But wait a minute, I'm looking for dy dt. I still don't have x. What do I do? Well, I got to find x. How am I going to do that? I'm going to come back to this point at which when y equals 3, x equals what? I don't know, but I do know the Pythagorean theorem. And I still have this side equal to 10. So basically I'm plugging in here for y equals 3 and solving for x. So I get x squared plus 3 squared equals 10 squared. So x squared equals 100 minus 9, which is 91. So x is equal to the square root of 91. We're going to use the exact answer for right now. Square root of 91 feet. Okay, somewhere a little bit less than 10, about maybe 9.5 feet. And so let's plug that in and solve for dy dt. So we get 6 dy dt equals 2 times a quarter is 1/2, so we get negative square root of 91 over 2. We got to divide both sides by 6. And so we get dy dt equals, plug this into your calculator, and we get about 0.8 feet per second. Remember that we changed to feet per second because these measurements were in feet, so we got to keep that in there. But it's negative 0.8 feet per second. That makes sense because it's going down once again. Okay, and again, negative makes sense, and that's your answer. Make sure you've got units with your answers. Word problems get word answers. Okay. So that's the process for solving related rates. Again, I'll do a couple of other example problems in another video for you guys. Those of you that need it, some of you guys are ready to jump right into my math lab or try a few problems on your own, and go ahead and do that. The key is that you've got to have an equation that you can differentiate with respect to t. So if it's not given, then it's going to be something very basic geometric. That's the best thing about these word problems in this section, is that you don't have to come up with the equations. They're going to be volume of a sphere, area of a rectangle, sides of a right triangle, something like that, where you're either going to have given the geometric formula or it's going to be very obvious. Okay? So that's good. You don't have to come up with your own equation, and then you differentiate, but you do differentiate it before you can do much with anything. Okay? So good luck with that, and let me know if you have any questions. Thanks.